If you saw the last video, then you'll know how transistors work, what they are, what they're made of, and why they're super useful for making computers do everything they do. And you'll also know that the function of a single transistor is pretty limited. It can amplify weak current, but that's about it. Its output is equal to its input, and that really gets us nowhere at all. Today we're going to see that by combining just a few transistors, we can start to do far more interesting things. Today we're going to look at logic gates. In previous videos, we have talked about high and low voltage, current or no current, and ones and zeros as the essence of digital computing. High voltage is 1, low voltage is 0. But now we're going to introduce a third way of talking about this binary divide. We're going to think about 1, high, as true, a truthy value, and 0 or low as a falsy value. To programmers, this will feel quite familiar. 0 is false and 1 is true. And the reason we want to introduce this third way of thinking about our binary data is that there is an entire field of mathematics dedicated to operating on the binary values true and false. In the mid-1800s, a mathematician called George Boole developed the field of Boolean algebra. Boolean algebra defines the set of operations which can be performed against true and false values and the logical outcomes of those operations. Today, we call true and false values Boole or Boolean values in George's honour, and this will be very familiar to programmers. And according to Boolean algebra, there are 3 basic operations which we can perform on the values true and false. Firstly, there is the NOT operation. The truth table of a NOT operation looks like this. If the input is true, the output is false. If the input is false, the output is true. For obvious reasons, this operation is sometimes referred to as inversion. The question this operation asks is the input not true? Next, there is the AND operation. The AND operation takes 2 or more inputs, and it asks, are all inputs true? If they are all true, the output is true. But if even one is false, then the output is false. So the question AND asks is this input and this input and this input true? And so on. Thirdly, there is the OR operation, which again takes 2 or more inputs. This outputs true if any of the inputs are true, and only if all inputs are false does it output false. And those are the 3 fundamental operations of Boolean algebra. But you're probably wondering, what on earth does this have to do with computing? Well, everything, but we'll get there. When early electrical engineers started working with transistors, they realised that if they thought about this high and low voltage as true and false or Boolean values, they could leverage Boolean algebra. And they realised that with just a few transistors, they could perform each of these basic operations set out by Boolean algebra. And these became what we now call the logic gates. So my first attempt at drawing these diagrams went terribly, and the later ones aren't much better. So I'm sorry about the drawings, but here we go. Here's how we build all 3 logical operations from Boolean algebra using nothing but transistors. The NOT gate actually only uses a single transistor, but with a modification to the setup we've used previously. For this gate, instead of thinking about the emitter as our output, we add an offshoot wire from the collector, and this wire becomes what we look at as the output. The consequence of this is that when the base goes high, the input is high, current now flows from the collector through to the emitter, and not through the offshoot wire. That means that the offshoot as our new output actually is low when the base is high. Conversely, if the base, our input, is low, current can't pass from the collector to the emitter, and instead flows down the offshoot wire, and our output is high when our input is low. And here's our NOT gate. You can see power going through this button and this LED to the base of the transistor. On the right hand side, the output of the emitter goes to ground as it has no relevance to this circuit. And you can see on the other side that the collector is connected to power and through this LED, which acts as our output offshoot wire. You can see that it's on at the moment while our input is off. So our output is high when our input is low. And when we press this button and current flows through the input, as you can see with the red LED, our output goes low. We've made an inverter. Next, we need an AND operation, an AND gate. Remember that AND operations accept 2 or more inputs, and we'll need a transistor for each input. For example, let's say we only have 2 inputs, so 2 transistors. By connecting them in series, the output of the first connecting to the collector of the second, we can test that all inputs are high. If just one is low, current will not be able to pass through that transistor and down to the rest of the chain. And only if all inputs are true will the output be high at the end of the chain. It's easy to see how this would expand to allow for more inputs by simply extending the chain of transistors. And this is what our AND gate looks like. On either side you can see from power, we're running through the button, through this resistor and into the base of the transistor. The same on the right hand side, from power through this button to the base. And on the far side you can see that this yellow wire connects the emitter of one transistor to the collector of the next in the chain. And this green LED is connected to the emitter of the final transistor in the chain and represents the output of the AND gate. So now, if we take one input high, the output stays low. And the same with the other input. Only when both inputs go high does the output go high. That's an AND gate. Finally, we need to build an OR gate, an operation to test if any of our inputs are high. Again, we need to take a transistor for each input and organize them in a parallel circuit, where the output is the point where they all converge. If any single of our inputs is high, current is able to flow through and output high. And here's our OR gate in metal. Each input is wired through a button to the base. Each transistor is wired separately, and then the current from each emitter converges on this green LED here, which is the output. Now by pressing either button, taking either or both inputs high, we see a high output. And that is our OR gate. And those are the logic gates, which enable us to perform logical operations using nothing more than electricity. Computers are formed of very little else but these 3 logical operations performed by the gates that we've just looked at. And we can compose these logical operations to do every operation that we could possibly want to do inside a computer. And we'll see an example of this in the next video. But for now, this has been 54M, and I'll see you soon.